Distillation, or fractionation, is the process of separating a mixture of two or more volatile substances into its components by utilizing the differences in the boiling point of each of the components. Gas absorption is an operation in which a gas mixture is contacted with a liquid for the purpose of preferentially dissolving one or more components of the gas. The phenomena of two-phase flow on the tray, as well as in the downcomers of commercial scale fractionators, will be described and illustrated. The various parameters encountered in the operation of fractionating trays are analyzed to give deeper insight and understanding to engineers engaged in the design or operation of fractionation devices. There are numerous designs of fractionating devices in the industry. They can be broadly classified as the trays with downcomers, trays without downcomers, and packings. The scope of this film will be confined to trays with downcomers. A typical tray consists of the bubbling area, the downcomer seal area, and the downcomer area. The tray is usually equipped with an outlet weir on the downstream side of the bubbling area. Liquid descending from the tray above through the downcomer changes direction at the downcomer seal area and enters the bubbling area. Here the liquid comes in contact with the vapor ascending through the tray. The outlet weir serves primarily to maintain a liquid level on the tray, as well as to provide a seal for the downcomer. Trays with downcomers may be designed to have a single path for the liquid, or they may have two or more paths if the liquid rate is much higher. In a cross-flowing tray, the bubbling area can be fitted with various types of devices, such as valves, bubble caps, or the holes of a sieve tray. The bubble cap tray was a favorite of the industry for a long time. There are still many in use throughout the industry. A properly designed bubble cap tray can have an almost limitless turn-down ratio. That is, this tray can be operated down to near zero vapor rate without a significant loss in its performance. Here, a bubble cap tray is operating at 10% of the flooding rate. Today, sieve trays are one of the widely used devices in the industry. Sieve trays are simple to design with the current state-of-the-art. They can be operated with considerable confidence for most ranges of operation. These are typical scenes of a sieve tray in action. Here, a sieve tray is operating at approximately 30% of the maximum rate. There is no weeping of liquid from the tray above, even at this low rate. Now, let's examine the valve trays. There are several valve tray designs available to the users from several manufacturers. Basically, valve trays are sieve trays with movable valves installed above the perforations. They can be designed to have high capacity and a wide operating range with good separating efficiency. Here are scenes of valve trays in operation. This is a tray equipped with circular valves. This tray is equipped with rectangular valves. behavior of the vapor-liquid mixture on the tray covers a wide range of flow regimes from bubbly to spray conditions, depending on the systems and operating conditions. This is a typical operating diagram. The horizontal axis represents the liquid rate, and the vertical axis represents the vapor rate. Of the various regimes of flow, the spray regime is likely to exist at the low liquid rate and high vapor rate region. Distillation performed under vacuum conditions is usually operating in the spray regime. The bubbly regime exists at the high liquid rate region. Here, the vapor-liquid contacting is taking place under bubbly or frothy conditions. This appearance is typical of high-pressure distillation. The intermediate region is the mixed regime, where the two-phase phenomena cannot clearly be defined as either spray or bubbly. The maximum operating limit is known as flooding. The flood point is defined as a condition where the combination of vapor and liquid traffic in the column is such that an incremental increase in the vapor rate will make the column inoperable, either due to massive entrainment or a downcomer limitation. The massive entrainment flood usually occurs in the low to moderate liquid rate region or in the spray regime. Entrainment flood may also be called a spray height flood. At the low to moderate liquid rates, the spray height increases as the vapor rate is increased. When the vapor rate is continually increased, the spray reaches the tray above, and some of the liquid is aspirated into the tray as entrainment. When the vapor rate is increased further, the average spray height increases above the tray spacing, and massive entrainment begins to take place, causing the trays and column to flood. There are several ways to increase the capacity of a tray that is being limited by entrainment. One way is to lower the effective pressure drop of a tray. With a sieve tray, this can be achieved by either increasing the hole area or by decreasing the hole diameter. Another way is to increase the bubbling area if the downcomer area is not already restricting the design. Finally, a higher capacity may be obtained by increasing the tray spacing. Downcomer flooding is caused by an entirely different mechanism than entrainment flood. It usually occurs at higher liquid rates. The cause of flooding is that the downcomer cannot accommodate the vapor-liquid mixture entering the downcomer, and finally backs up on the tray above. Let us examine the mechanism of downcomer hydraulics to get a clearer understanding of the downcomer flood. The downcomer will become flooded when the aerated frothy liquid fills the downcomer. The height of the frothy liquid is a function of the height and frothiness of the liquid in the downcomer. The clear liquid backed up in the downcomer is caused by three factors. One, the clear liquid height at the inlet edge of the tray. This is a function of the weir height and the liquid rate. Two, the total tray pressure drop. This causes the liquid to back up in the downcomer, since the vapor force necessary to overcome the tray pressure drop will also be restricting the liquid leaving the downcomer. Tray pressure drop is a function of the tray geometry and the vapor and liquid rates. And 3, the head loss due to the flow of liquid under the downcomer. This is a function of the geometry of the downcomer escape area and the liquid rate. If the tray design indicates that the downcomer capacity is inadequate, several variables can be analyzed to attempt to increase the downcomer capacity. In order to increase the downcomer capacity, the effective clear liquid height in the downcomer must be lowered. The inlet clear liquid height can be lowered by decreasing the weir height or by lengthening the weir length. The tray pressure drop can be lowered by installing lower pressure drop devices in the bubbling area or by lowering or lengthening the outlet weir. And the head loss under the downcomer can be lowered either by increasing the area under the downcomer or by shaping the outlet edge of the downcomer to obtain a streamlined flow for the exiting liquid. However, if the liquid height in the downcomer cannot be lowered to the desired height by conventional means, it is possible to split the flow of liquid into 2 or more paths and obtain the desired results. Splitting the flow path results in larger area under the downcomer, longer outlet weir length, and lower clear liquid height on the tray, all of which will contribute towards lowering the liquid height in the downcomer. Another type of downcomer flooding is due to the downcomer entrance area being inadequate for the amount of liquid entering. This is especially true when the liquid is foaming. The solution for this problem is to provide a larger downcomer area at the top. This must be done at the risk of some loss in the bubbling area. However, the loss in the bubbling area may be minimized if the downcomer is sloped from top to bottom. In the preceding section, the capacity of the tray has been examined, namely flooding due to high entrainment and limitations in the downcomer. We have observed ways of improving the capacity by modifying the tray design. However, there is a certain vapor and liquid rate beyond which a tray can no longer be operated, regardless of the hardware design improvement or increase in tray spacing. This phenomena is called flooding by system limitation. This occurs when there is substantial net upward flow of liquid relative to the total liquid flow and is a function of the terminal velocity of the liquid drops populating the inter-tray space. This phenomena is more frequently encountered with the high-pressure systems. However, it may occur with any system. So far, we have been discussing the capacity of the tray in terms of the hydraulic limitations. That is, we have been examining the point where the tray cannot tolerate any additional vapor or liquid. Before the hydraulic capacity is reached, the mass transfer efficiency may become so poor that operation beyond a certain rate may become impractical. This condition may be caused by entrainment from tray to tray. The line on the graph shows the tray efficiency values over the optimum operating range. As the vapor rate is increased, entrainment begins to set in as shown by the red line. And with the increase in entrainment rate, the tray begins to perform less efficiently. It is important to consider the amount of entrainment a tray can tolerate to determine the upper operating limit. Next, the lower operating limits of a distillation tray will be examined. Most trays must be operated above a certain rate to obtain satisfactory performance. This is particularly true with sieve trays. Sieve trays will begin to weep when the vapor rate is lowered beyond a certain point. This is the weep point of a sieve tray. The weep point is a function of the tray geometry and the physical properties of the system. When the vapor rate is reduced further, the sieve tray will begin to weep more and lower the separation efficiency. Experiments have shown, however, that an appreciable amount of weeping, as much as 20% of the liquid, will not necessarily be harmful to the separation efficiency. Weeping of sieve trays may be reduced or eliminated by lowering the whole area of the tray. However, the lower hole area may result in lowering of the capacity of the tray. When the vapor rate is further lowered, the weeping will become extremely severe and reach a point where all of the liquid weeps through the tray and none of the liquid is going over the weir. This is known as the dump point. Examination of various types of devices will show that not all devices have the same capacity or upper operating limits. For example, device A may have a high capacity at the lower liquid rates, but a low capacity at high liquid rates. Device B, on the other hand, may have a fairly constant capacity regardless of the liquid rate. And other devices may have different capacity characteristics depending on the design of the device. The same may be said about the lower operating limits. A high hole area sieve tray may have a relatively high weep point and dump point. And a tightly sealed bubble cap or valve tray may have a negligible lower limit. The lower limits of other devices will depend on the design characteristics under consideration. Therefore, it is important to select a device that will give a suitable range of operation for the desired mass transfer conditions. The foregoing studies have shown how the various design parameters of cross-flowing trays can be combined to give a viable tray design, and how to cope with design limitations. Furthermore, this film has attempted to show that no single tray design can be adapted to all situations, and that care must be exercised in choosing the proper components for an optimum design. Research is continuing on the various parameters encountered in fractionating devices to give deeper insight and understanding to engineers engaged in the design or operation of fractionation equipment.